Hello, this is Rick from MathX, and today we'll be taking on number 15 from the 2019 AIME I. Now, this is a hard problem, no doubt about it, but that doesn't mean we should not try solving this problem at all. As I'm about to show you, even though this problem is hard, it's not untouchable, and that if we go about it the right way and try our best, even we can solve this problem, no matter our level in math. So without further ado, let's just jump into this problem to explore its inner beauty. Let AB be a chord of circle omega. Let P be a point on the chord AB. Circle omega 1 passes through A and P and is internally tangent to omega. Circle omega 2 passes through B and P and is internally tangent to omega. Circles omega 1 and omega 2 intersect at points P and Q. Line PQ intersects omega at x and y. Assume that AP equals 5, PB equals 3, and XY equals 11. And PQ squared is equal to M over N, where M and N are relatively prime positive integers. Find M plus N. So this problem overloads us with a lot of information. And in the style of geometry, it just tells us a lot of relationships. So the first step to attack this problem is just try to draw out what it's telling us as best as possible. So let's start from the beginning. It talks to us about a circle omega. It tells us that the circle omega has a chord AB. It tells us then that there is a point P on the chord AB. It then tells us that a smaller circle, omega 1, passes through A and P and is internally tangent to omega. So inside this circle, we have to make a circle that goes through A and P. And if it goes through A and P and no other part of omega, then it already then is internally tangent to omega. So we just need to find a way to draw a circle inside this bigger circle, omega, such that it only touches A and goes through P. So here I kind of did that. Then we have another circle, circle omega 2, and it passes through B and P and is internally tangent to omega. Once again, the same way with omega 1, in order for it to be internally tangent to omega, we just need to make sure that the circle omega 2 will run through B and P and not intersect omega at any other points. So we can draw another circle satisfying that condition. So here I've done that. I've drawn the circle omega 2. And it tells us that circles omega 1 and omega 2 intersect at points P and Q. Here we can see that they both intersect at P because they're both supposed to run through it. And we see another point that they intersect at, so we can label this as Q. Then it tells us that this line, PQ, must also intersect the larger circle, circle omega, at x and y. So we can extend PQ so that it intersects the circle at 2 points, x and y. And just like that, we're done. Now, the problem also tells us some lengths. But our diagram is getting overwhelmed. So it'd be wise to just keep the lengths off to the side so that we can understand our diagram without it getting messy. So we can write all this information that it tells us off over to the side. AP is equal to 5, PB is equal to 3, and XY is equal to 11. And our goal is to find out what PQ squared is in terms of M over N, and then add M over N. So with our diagram drawn out and all our information stored to the side, we can officially start doing this problem. Now the first thing that sticks out to me with the lengths of all these different parts of chords is using power of point. Power of point is a method to determine the product of different parts of chords based on the common point they go through. So if we write a PowerPoint equation for the point P, we can write AP times BP is equal to XP times YP. And this formula is derived using some similarity, but nonetheless, it's going to be a vital tool in finding out what XP and YP are, and then exploiting those values to find out what PQ is. So in this equation, we know what the entire left-hand side is. We know that AP is 5, and that BP or PB is 3. So AP times BP would be equal to 5 times 3, which is 15. But on the right-hand side, we don't know any values. We don't know what XP is, or we don't know what YP is. But we do know their relationship with one another. We know that XP plus PY will give us XY. And here we see that XY is equal to 11. So if we denote XP as X, we can denote YP as 11 minus X, so that they both sum up to 11. So if we write XP as X, YP will be 11 minus X. And using the PowerPoint formula, we know that these two will multiply up to 15. So if we expand the right-hand side, we get 15 is equal to 11x minus x squared. Now if we bring the x squared and 11x to the other side, we see that x squared minus 11x plus 15 is equal to 0. Now we can't use midterm factoring on this quadratic, because if we try that, we see that we can't really break up this middle term to be factorable. So we have to factor this quadratic the other way, using the quadratic formula. And we get that this gives us the two roots to our quadratic, x squared minus 11x plus 15. So these are our two solutions for x. This isn't simplified though, so we can write x more concisely as 11 plus minus the square root of 61 over 2. Now, this might be slightly confusing because we were searching for the length of xp, and we denoted that as x. So we can't have two different lengths for xp. But we see that this works out because this solution of x will give us the length of xp and yp. As we see, when we add each of these solutions with one another, 11 plus root 61 over 2 plus 11 minus root 61 over 2, we get two numbers that will add up to 11 but multiply to 15. So that means the smaller root in this case is xp, while the larger root is yp. So you can write that off here. xp is equal to the smaller root, which is 11 minus root 61 over 2, and yp is the bigger root, 11 plus root 61 over 2. So now we have the lengths of xp and yp. But that doesn't really help us that much in this problem, because we're supposed to find out what PQ is, and we don't really have any leads on that. However, we see one thing. PQ is equal to XQ minus XP, because when we subtract the two, we get what's left over, which in this case is PQ. So we can write PQ as XQ minus XP. Now we already know what XP is. We've already found XP to be 11 minus root 61 over 2. So if we find out what XQ is, we can subtract XP from it and get the value of PQ. So let's try to figure out what XQ is. Now, this is where the problem gets really difficult. Because we could just eyeball it and say that, well, XQ kind of looks like the midpoint of XY. But we're dealing with the AIME test, and we can't make assumptions like that. Everything we do in geometry, we have to prove. So we can go and try to prove that XQ is the midpoint of XY. And using that, we'll find the length of XQ, subtract that from XP to get PQ. So we just have to prove that XQ is the midpoint of XY. Now, we're dealing with a circle. So In order to find different lengths, I think it would be helpful to draw a cyclic quadrilateral. And I propose to do this by drawing a line from A through Q to intersect the larger circle omega. And we can name the intersection between this line through AQ and the circle omega as U. We can do the same thing with B. We can extend a line from B through Q and on the other side of circle omega. And we can label the intersection of this line BQ with the circle omega as V. Now, what we just carried out by extending this line from B through Q to intersect the larger circle omega is known as a homothency. A homothency is a transformation that dilates distances with respect to a fixed point. And this is just fancy way of saying enlarging something or scaling it down by a certain factor. With the case of the segment BQ, we've we've essentially enlarged the segment BQ as if the segment BQ was in the larger circle omega. Whatever BQ is in proportion to the smaller circle omega 2, it is the same thing with respect to the larger circle omega. So we've essentially just scaled up the larger circle omega 2, and we've scaled it up to the size of omega. So that's why BQ is now BV. If we do the same thing with PQ and enlarge this to the scale of the larger circle omega, we would get the line segment AV. As AV is merely just an enlargement of the already pre-existing PQ, it also is parallel to PQ, as we've done nothing to PQ or BQ or the circle omega 2. We've just enlarged it to the scale of omega. And using that, we can deduce that since nothing has happened except these lines have been enlarged, AV and PQ are parallel. We can do the same thing with the segment BU. Just like how I did with the segment BQ to V, the extension from segment AQ to U was also a homothency, as by doing so, we've just merely scaled up the pre-existing segment AQ to if it were the size of omega. Whatever AQ is to the smaller circle omega 1, AU is to the larger circle omega. We've done nothing but scale it up. And if we connect the lines, we see that it is the same thing with PQ and BU. We've done nothing but scale it up. So just like how AV was parallel to PQ, because AV was just a homothency of PQ, BU is once again just an homothency, an enlargement of PQ. And both of these lines are parallel to PQ. We see that since BU is parallel to PQ and AV is parallel to PQ, AV is parallel to BU. That sets up for something interesting because that means that because of VB, angles AVB and angles VBU would be congruent because alternate interior angles of parallel lines are congruent. But then it would also set up for angles VAU and angles VBU to be congruent because both of these angles intercept the same arc. So since we see that angles VAU and angles VBU are congruent, and angles VBU and angles AVB are congruent, we see that angles VAU and AVB are congruent. meaning that this triangle QAV, is an isosceles triangle. We can see the same thing with triangle QBU, as just like with triangle VAU, angles AVB and angles BUA both intercept the same arc, meaning that their measures are congruent. And angles AVB is congruent to angles VBU because of alternate interior angles. So we get another pair of congruent angles, meaning another pair of congruent sides. So we get two isosceles triangles, QAV and QBU. Now, the deal with isosceles triangles is they are essentially one right triangle flipped over the altitude to the unequal side. Meaning that if we drop an altitude from this Q to the side AV and label this the point where the altitude hits AV as T, triangle ATQ and triangle VQT are the same triangle, but reflected over the line TQ. So if we apply this idea that they're the same but reflected over a line, we see that that means that XQ and QY are the same but reflected over the line TQ, thus proving that Q is the midpoint of XY. So if Q is the midpoint of XY, that means that XQ is going to be half of XY. And since we've already established XY to be 11, XQ would equal to 11 over 2. So now we have everything we need to solve for PQ. PQ would equal to 11 over 2 minus 11 minus root 61 over 2. If we distribute the negative across the parentheses, we get PQ is equal to 11 over 2 minus 11 over 2 plus 61 root 61 over 2. So we get PQ is equal to root 61 over 2. Now to get what PQ squared is, we just need to square this. So PQ squared is equal to root 61 over 2 whole squared. Root 61 squared will give us 61, and 2 squared will give us 4. So then if we want to find m plus n, where m over n is equal to 61 over 4, well, m plus n is just equal to 61 plus 4. And 61 plus 4 is 65, giving us our end answer. Now this problem was incredibly hard. Probably one of, if not the hardest problem I've ever covered on my channel. But we've solved it. This AIME problem was the final problem in an AIME test. And it was quite difficult. But we figured out the elegant solution just by persevering and going through it. So, this just goes to show that even if you can't solve a problem on a test, you should look over it after, as we can learn a lot just by doing this problem. I surely learned a lot while researching the solution for this problem. So, after a test, always go over the problems that you've missed on a test, as that's the only way you can improve. We don't get better by reviewing all the stuff we already know. We get better by attacking the stuff we're uncomfortable with, showing that in order to truly improve, we must keep on practicing and just keep on doing math.